Hello, everyone. This is Professor DePaulo welcoming you back to Psych 220 Behavioral Statistics. And today I'm going to be talking about the correlated groups t-test. So we already covered the single sample t-test. So we're going to do and we did the independent groups t-test where the groups are different. We're going to do the correlated groups t-test today where the groups are made up of the same individuals almost all the time. There is a situation where it's not the case, but 99% of the time, correlated groups t-test is known as a repeated measures t. So repeated measures t-test always has two groups. So all the t-tests are always comparing two groups, whether it's a single sample to a population mean, or two different samples in the independent groups t-test, or two related samples, like the same individual before and after. So this is the most common, right? So it's before and after. We're measuring the same individuals. So the same individuals that you have at time one are being measured at time two, and then you're looking for a difference. So this is common for intervention like study. So you do the before, then you do the intervention, and then you measure the after. And you determine if the intervention affects the scores, right? So this person scored a certain amount at the beginning, then you did some intervention, and I've done this correlated groups t-test frequently, where I give an intervention like meditation training, and then we look at scores of anxiety and depression before meditation training, and then after, right? So it's anxiety and depression before. So this is kind of what I have done in the past. Then we give the meditation for 10 weeks. We give training by professionals. And then we look at anxiety and depression afterwards. And we hypothesize to see a decrease, right? And then we can say that the difference is due to the meditation. And then I can make this more complicated by giving some people meditation and some people something else. So I give meditation to one group and stress management to the other group, and I can see if meditation leads to bigger decreases than, say, stress management. And so that would be kind of a mix between independent and correlated groups. So it's a mixed design. But if we're just focusing on correlated groups, we do the before, anxiety and depression. We do the intervention, meditation, 10 weeks. And then we do the after, anxiety and depression. And there are problems with the correlated groups t-test, right? The biggest problem is subject mortality. So now that doesn't mean that the subjects die, although I guess they could. You would hope not to be the case. But subject mortality just means subject loss. So you give the before, and then you do the intervention, and then you hope that they come for the after, right? But they don't show up. So you have their before score, but you have no after score, and now you have to eliminate them from the study because they're gone. And the bigger the gap here, the longer you have them wait, the more likely they're going to disappear. So that's subject mortality, and that's a big problem with this correlated groups t-test. If you're doing it before and after, it's an issue because people don't show up. People get bored, they get busy, and then you have no data, right? So if I could do the test, like if I do independent groups t-test, I test them at the same time, only at one time. I'm not doing before and after. So the less time you have between outcomes or between measures, the better. Now I've seen what these are also called longitudinal studies. I've seen some of these longitudinal studies where they look at cohorts, like groups of people recruited together, and it's over a period of years. Now that to me is really extremely challenging because you have to put a lot of effort and probably money into maintaining contact with these participants over long periods of time. So these are difficult studies to do. You'd rather this time period be as minimal as possible. You also have things like maturation that play a role, uh, or history effect. So if you take research methods, you probably are learning about these things, maturation or history effect, in that things change. So over those 10 weeks, things change, right? So something happens. Maybe you do this meditation study, and then during those 10 weeks, the participant fails a class, or they get fired from their job, or something happens in their personal life. Well, that's an effect of history. So something is intervening, and that's going to affect the results of the study. So can I really tell the difference if some kind of significant event happens between the before and after? That significant event is going to alter the study. Or even maturation, like, this is more common when we have multiple sessions and the participant gets tired because you're giving them multiple sessions. Right? There's a whole bunch of other ones. There's instrumentation, but these are the most common ones. And history is a big problem. You also have order effects, where the order in which you complete the different conditions can play a role. And then those order effects can be reduced by something called counterbalancing, the order in which participants partake in the multiple conditions of your study. That's not really a big problem unless you're doing, multiple conditions. And you wouldn't be doing multiple conditions with a t-test. T-test is only two groups, so only two conditions, before and after. There are no multiple conditions with a t-test. Now, some of the other assumptions of the t-test. So some of this stuff, history, maturation effect, this is more a research methods question, but I just want you to be aware that if something happens between before and after in the time period in between, that you're going to have a problem analyzing the data. Some of the assumptions of this correlated groups t-test is that the data must be correlated. And the data will be correlated if you're using the same people. So if the same individual does before and then they do after, those measures are correlated because it's the same individual. So this data must be correlated. It must be related. They must go together, right? Otherwise, something's wrong because they should be the same people. The difference scores should be normally distributed. So with this correlated group t-test, we are computing difference scores. Those difference scores should be normally distributed. What are the difference scores? Well, it's usually before minus after. This is traditionally the difference scores. So you do before minus after, and you get a set of scores called the difference scores. Those set of difference scores should be normally distributed, relatively normally distributed. Now, it plays a bigger part that they're normally distributed if your sample is small. If your sample is large, it's not as big of an issue. But if you have a small sample and you have outliers, in the difference scores, some that, like, for example, like the before minus after is gigantic for a few people and much less, much smaller for a lot of the majority of other people. So if you have these big outliers and difference scores, you're going to have a skewed distribution of different scores, and it's going to be a problem if you have a small sample. If you have a large sample, not a big issue. This correlated groups t-test is what's called robust. So you're able to violate the normality assumption, and it's okay if you have a big sample. If you have a small sample, you're going to be more cognizant of the normal distribution of different scores. So data must be correlated and the different scores must be normally distributed. There is no homogeneity of variance assumption. There is no homogeneity of variance assumption. Remember, in the independent groups t-test, we wanted the population variances. They were assumed to be relatively equal, right? The larger variance should be no more than 4 times the smaller variance. That was for independent groups T. For correlated groups T, we don't have to worry about homogeneity of variance because we're only looking at one variance, and that's the variance of the difference scores. We're not looking at 2 groups, we're looking at one. We are technically looking at before and after, but when we compute the difference scores, we convert those 2 groups into one group of scores that we're interested in. So this becomes very similar to the single sample T. So this is very similar to single sample T because our single sample here is the difference scores. So the difference scores is like one sample. And we're always comparing it to 0. So the null hypothesis is that the difference scores are 0. There's no difference between before and after. And then the alternative is that the difference scores are greater than or less than or different than 0, right? So we're really comparing one sample of difference scores to a value of 0. 0 represents the null hypothesis. So in this way, it's very similar to the single sample t-test. The formula is a little bit different because we're looking at different scores, but it's pretty much the same as a single sample t. And we also know the degrees of freedom. So the df is n minus 1. N is the number of pairs of scores. So it's the number of pairs of scores minus 1. So that n minus 1, is the number of pairs of score minus 1, or you could think of it as the number of different scores minus 1. Either way is correct. So let's take a look at a problem here that I've given you through the worksheets. So here's our first problem. I'm just going to copy and paste it into the whiteboard here. And let's make it a little bit easier to read. Okay, here we go. To motivate citizens to conserve gasoline, the government's considering mounting a nationwide conservation campaign. However, before we do this, on a national level, it decides to conduct an experiment to evaluate the effectiveness of the campaign. For the experiment, the conservation campaign is conducted in a small but representative geographical area. 9 families are randomly selected from the area, and the amount of gasoline they use is monitored for 1 month before the advertising campaign and for 1 month after the campaign. So we're looking at conservation. How effective is the conservation campaign? Conservation means using less gasoline. So the null is obviously no difference. No difference in gasoline consumed. No difference in gasoline consumed after the campaign, right? So basically the before and the after is going to be 0. Before minus after is 0. There's no difference before the campaign and after the campaign, which means the campaign didn't do anything. The alternative here, we're looking at, is the campaign effective? Is it reducing gasoline? So gasoline use should be reduced after the campaign. So after watching or viewing the campaign or being, exposed to the campaign at some reason, there should be less gasoline use. So let's look to test this hypothesis by looking at the before and the after of the data, the repeated measures. So we're going to have a before column and we're going to have an after column. Now you want to line these up the best you can. It makes a difference. You want to line up the before and the after because it's the same person. So each row here is a different individual. And each individual has two scores, before and after. So you want to line them up because it's the same person. So this person scored 55 before on gas use and then 52 after. And we're just going to list all the scores here, before and after. We're doing the before and after still. Line them up as best as you can. So now that we have the before and after, we have how many pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs of scores. So 9 people. We need to make a difference column. So I'm going to call that D. And we're going to do before minus after. I like to keep it that way all the time so you don't get confused. You can do it after minus before, but you got to keep everything consistent. So I'd rather always do before minus after so we know what direction we're always going in or we're looking in. Now, if after, according to the alternative hypothesis, the research hypothesis, after should be lower than before. So we're hypothesizing that after is lower than before because that means that less gas was used. That's what we're looking for. So if after is hypothesized to be lower than before, then if I do before minus after, I should get a positive value. Right. So if my hypothesis is correct or is supported, before minus after should be a positive difference score. So let's do that, before minus after. Now you may get negative values and then, so be very careful about how you're dealing with the negative values if you get them. Not really in this problem, but in future problems, you may get negative values. Here, we're looking in the right direction, pretty much. We're getting mostly positive values here. Here's a negative. Sometimes we get negative values and you have to deal with negatives. And I try to make that as painless as possible, but so there you have it. So those are our different scores. We are then going to add up those different scores. So this is going to be the sum of the different scores or sum of D, and this adds to 36. Now we need to compute the mean of the different scores. So mean sub D, that's sum of D over N, where N is the number of pairs of scores or the number of different scores. So here it's going to be 36, and we have 9 different scores, and our mean is going to be 4. So the mean of the different scores is 4. Now we need to find the sum of squares of the different scores. Now remember, this is like calculating variance, and there are 2 ways to do it. So you could do sum of squares D as the sum of D minus mean of D squared, right? And that'll give you the sum of squares of the different scores that way. This is a D, by the way, in case you think this is a key, it's a D. So let me write that a little better. Now this works fine. You could take these different scores, subtract 4 from each of these different scores and square it and find the sum of squares this way, add up the column, right? The only problem with this method here is that sometimes you have negatives. So then you have negatives minus a positive, or negatives minus a negative, and then you have to square it. And when students get negatives minus negatives, there's a potential for a screw up. So I actually don't like this method for students because a lot of students struggle with negatives, negative values. So I prefer to do it the other way, not the this is the deviation score way. I prefer to do it as the other way, the computational way, which is the sum of d squared minus the sum of d squared over n. Remember, this is similar to the x when we did variance previously, where it was x squared minus sum of x squared over n. All we're doing is substituting d in here for x. So I prefer to do it the way with the d squares because this gets rid of the negatives for the most part. So you don't have to worry about doing negatives minus negatives and squaring that difference. So I'm going to do it this way for these kind of problems. So I'm going to make a d squared column. But if you want to do it the first way and you're comfortable using negatives and subtracting negatives and all that stuff, you could do it this way. But I find that there are some students that just screw up the negatives. So it's probably better to do it the second way. Let's make a d squared column, square these values. Now this will turn everything positive, which is what I think a lot of people like, working with positive numbers rather than negative numbers. And then we're going to add up this column of all positives. And we get 300. So this is the sum of d squared. We got 332. And now we're ready to plug into the formula, the second formula we're using here. So sum of squares of the difference scores is sum of d squared, which is 332, minus sum of d, which is 36 squared, over n, which is 9. So simplifying this, 332 minus, we do 36 squared over 9, we get 144. And that's going to be equal to 188. So the sum of squares of the different scores is 188. Now we have to find the standard deviation because we're going to have to plug into t. And this t is just like the single sample t. So t is going to be the mean of the difference scores on top divided by the standard error of the difference scores, which is the standard deviation of the different scores divided by the square root of n, where n is the number of different scores, or n is the number of pairs of scores, whatever you prefer. So remember, this looks exactly like the single sample formula, but instead of x, we have d. But it's computed the same exact way as the single sample t-test. So we got to find the variance first, and then we have to find the standard deviation. So the variance is going to be 188. So it's the sum of squares over n minus 1. So this is over 8. So we have to do 188 divided by 8 to find that variance. And for some reason, I don't have that pre-computed. So I'm going to go back to posit cloud, which is R, and do 188 over 8. I just skipped a step, but I'm going to do the intermediate step for you. So we're just waiting for this to load. This is what I use as my default calculator. Let's do 188 divided by 8. We get 23.5. So let's go back here. We get 23.5. Okay. And then we take the square root of this. And that gives us 4.85. So we're just going to do square root just to double check. There we go. Not sure why this is moving on me. Scroll back up. It just kind of brought me to the top for some reason. There we go. Okay, so we have that. So now we can plug into T. So T is the mean of the different scores. Now this is technically minus 0. But I don't have to write minus 0 because minus 0 is 0. So why write minus 0? But we're always comparing this mean of the different score to 0. Because under the null hypothesis, the different score should be 0. But I don't need to write minus 0 because it's just not necessary. So the mean of the different scores, which is 4 on top. On the bottom, we have the standard deviation over the square root of n. So the standard deviation is 4.85 over the square root of n. So 4.85 down here over the square root of 9, which we know is 3. So this is 4 over 4.85 over 3, which becomes 1.612. And then that gives me 2.48 rounded. You might be off by a touch if you're rounding differently, but you got to be around that number. 2.48 is our obtained t value. And now we got to look for our critical t. Our degrees of freedom is the number of scores minus 1, number of pairs of scores, or the number of different scores. So we have 9 pairs of scores minus 1 gives us 8. And so we need to find the critical value at, I think, 0.05 for this problem. Let's take a look. 0.05. So we're going to do a one-tailed test because we're looking for a reduction. Right? So is this campaign working to reduce gasoline? So we're looking at one-tailed, the reduction. We expect if the alternative hypothesis is supported, that after should be lower than before, right? So if after should be lower than before, then before minus after should be positive. We should have a positive before minus after, and we do. So the mean is showing us it's in the right direction. We're going to do a one-tailed at 0.05, and we're going to look at the critical value. So we find 0.05 one-tailed up at the top, and this is the t-table again. At the top, we look at one-tailed. The second row is two-tailed, so it's 0.05 one-tailed. And we go down to 8, and we get 1.860 positive because we expect before minus after to be positive, so we're looking for a positive critical value. 1.860 is our critical value. So our crit t is critical value is positive 1.860. And our obtained value is 2.48. Here's the t distribution. Here's our crit, 1.860. And in this tail is 2.48. So since the obtained value is in the tail, or the obtained value is more extreme than the critical value, we are then rejecting the null. And when we reject the null, we support the alternative, stating that this program, this conservation program, actually lowers gasoline consumption. So it works. We get lower gas consumption. And that's how you do the correlated groups T. It basically looks like a one sample T. So let's look at another problem. Problem 2. We are looking at IQ for this problem. So we're going to get the second problem here. These are available under the worksheet file folder in Brightspace. And this is looking at age, IQ and curiosity by age. So let's put it in here. So developmental psychologists at a prominent California university conducted a longitudinal study investigating if high levels of curiosity in early childhood increase intelligence later in life. 12 of the 3-year-olds scoring high on curiosity, whatever they've arbitrarily decided what's high on curiosity. We don't know how they did that, but they've determined a certain score is high on curiosity. And they took 12 of those 3-year-olds and they gave them an IQ test. They then waited 8 years. So this is an example of like a study that would be really difficult to do because they're giving an IQ at 3 years of age and then they're waiting 8 years and doing another IQ at 11. So it is a t test. It is a correlated groups t test because it's the same people at age 3 and age 11, right? It would just be very difficult to even retain most of those children. And I would not want to be doing this study because you have to follow up with these people constantly for 8 years. You can't just tell them, we're going to call you back in 8 years. Why? Because people get busy, people move, people forget about it. They 8 years is a long gap. So there's a lot of problems. Things happen in those 8 years that may alter the study. But if you could pull this off, it'd be really difficult to pull it off. But if you could pull it off, this is what it could look like, right? Here are the IQ scores. So we're going to do IQ at 3 and IQ at 11. We'll just move this over here. So let's do IQ at 3. And then we do IQ at 11. And these are the pairs. So each row represents one person, one child, whose IQ is taken at 3, and then whose IQ is taken then 8 years later at 11. Like I said, this would be a very difficult study, but there are people that do it. Just, I wouldn't want to do it. There's a lot of phone calls, a lot of emails, a lot of meetings with people over the years to try to retain the sample, right? You can't just expect people 8 years later to be available. You have to really stay in contact with them frequently for those 8 years, or you'll lose all those people. But this is their sample that they retain. See, when I did a study, a repeated measure study, and I waited 10 weeks, it was really difficult. People didn't want to, people forgot about it. They're too busy, they don't want to be involved anymore. And I can't imagine 8 years. This is 135. I'm sorry. I copied this wrong. It's 135. 135, 148. So all I'm doing is copying the two columns, 128, 139, 104, 122, 98, 117. Now let's look at this this problem again. So null, no difference in IQ score, right? So this idea that there'd be a difference in, in children with high levels of curiosity, they would end up with higher IQ scores as they get older. This idea, according to the null, doesn't work. So there's no difference in IQ score at 3 years and 11 years. And the alternative is there's an increase. So it's one tail, right? There is an increase. So it's one tailed in IQ scores. So age 11 IQ is higher than age 3 IQ. First, let's make the difference column. We're going to do it just like we did the last one. Make the difference column. and do the difference squares. And you see we get all these negative values, which is what I was talking about before. So we're doing before minus after. Could you do after minus before here? You could, but then you got to keep that in mind when you test the hypothesis. You're going to look in the other direction. I find it easier just always doing before minus after. I just think it's easier to do it one way all the time. So we're doing before minus after. And we're going to add those different scores up and get the sum of the different scores. Hold on, sum of different scores. And we do the sum of the different scores, we get negative 144. And now we got to do the d squared column. So we're squaring all these different scores. Now, once again, these are a little bit bigger calculations, but the good thing here is we're getting rid of all the negatives. So you don't have to worry about any negatives. This will be all positive or zero, this column. So you get rid of all the negatives. Otherwise, you'd have to do negative 14 minus the mean of the different scores, which I think is 12 here, negative 12. So you'd have to do negative 14 minus negative 12, negative 11 minus negative 12, negative 14 minus negative 12. And so you're getting a lot of negatives in there. That's a potential for a screw up. So if you do it the deviation score method where you subtract the mean from each of the d values, the mean of the d column, which is going to be negative 12 from each of these d values, you get a lot of negatives. And with those negatives, there's going to be errors. So this is probably an easier way because you get rid of all the negatives by just doing it this way and squaring each value. That's the rationale for doing it this way. But we get big numbers here, right? So these are bigger numbers, but they're all positive. So there's a trade-off. And we're going to add up all the d squared scores. And when we do that, we get 2394. So a big number there. Now we're going to plug in. So we need to find the mean of d. But as I said before, we could do that in our head because the sum of d is this thing's going a bit bonkers here. Sorry about that. This thing has gotten crazy here. Sometimes it does that occasionally where it just starts going crazy. And I gotta try to move this out of the way of this line here. So I don't think I can get rid of this line again. No, I just want to get rid of it that way. Maybe I can select it. Probably not. I want to clear this, but okay, that works better. I'm just trying to make this a little bit easier to navigate. Okay. So let's look at the formula. So we're going to do sum of squares of d, which is just simply the sum of d squared minus the sum of d, quantity squared, over n. So if we do that, we get the sum of d squared, which is 2394, minus this negative 144 squared over n. N is the number of pairs of scores. So 1, 2, 3, 4, 5, 6, 7, 8, 12. So this is 2394 minus 144 squared over 12. When we simplify negative 144 squared, it becomes a positive. Divide by 12 gives us 1728. And that total gives us 666. Uh-oh. Oh, that's pretty apprehensive there. So we got 666. Okay. I assure you, it's not an inherently evil problem. Uh, it's pure coincidence. Okay. So that's sum of squares of d. Now we need mean of d. So the mean of d is the sum of d over n. This is negative 144 over 12. This is negative 12. So the mean of d is negative 12, right? And now we're going to plug into the formula. We actually need the standard error, right? So this is the formula again. T equals the mean of d over the standard deviation of d divided by square root of n. So we need the standard deviation of d. So S of d, we got to first find the variance, or S squared of d. That's equal to the sum of squares of d over n minus 1, number of pairs of scores minus 1. So the sum of squares of d is 666. N minus 1, n is 12. 12 minus 1 is 11. And when we simplify, we get 60.55. That's our variance of the different scores. We have to take the square root of that to get the standard deviation of the different scores. Square root of 60.55. When we do that, we get 7.78. And now we can plug in here. So mean of the different scores is negative 12. The standard deviation is 7.78 divided by the square root of n, which is the square root of 12 here. So when I simplify, I get negative 12. When I do this division, 7.78 divided by square root of 12, I get 2.25 approximately. You may have some rounding error, it's okay. And that equals negative 5.33. That's my t value. Now, my degrees of freedom here is n minus 1, so that's 12 minus 1 is 11. And so I need to find the critical t, and we're looking at 0.01 here. So the critical value for this problem is 0.01, one-tailed. So we're going to go into the table. We're going to look at one-tailed, which is the top row, 0.01, with 11 degrees of freedom. If we scroll down, 11 degrees of freedom, and we get 0.01, 11 degrees of freedom. Well, it's just, this is, we're looking for an increase, right? So we're doing one tail, 2.718 positive, because we're looking for an increase, 2.718 at the 0.01, I think that is 0.01, right? 0.01, one-tailed. So we're looking at, let's get that number. Just be careful with looking at this here, because it's easy to, I'm doing it on the screen. It's a little bit harder to look at. 2.718 for 0.01, one-tailed. Positive 2.718. Here's our obtained value. Here's our critical value. Actually, the critical value is going to be negative because we expect after to be higher than before. So we expect, this is basically what we expect. We expect before minus after so we expect before minus after to be negative. Why do we expect before minus after to be negative? Because if IQ is increased, then the IQ of after is going to be greater than the IQ of before, right? So if I do a smaller IQ minus a larger IQ, I'm going to get a negative value. So since we expect before minus after to be negative, this has to be a negative critical value. So it's negative 2.718, and we're going to look at the negative tail. So it's always basically what you expect to happen under the alternative hypothesis, and that determines what the critical value is going to be. So let's look at that curve. Stupid line that I drew here that is a problem. It's annoying me. Way out here, we have negative 2.718, but our obtained value is way out here in the tail, negative 5.33. So our obtained value is more extreme than our critical value, so we're going to reject the null. We're rejecting the null here because our obtained value is more extreme than our critical value. So we reject the null hypothesis, and when we reject the null hypothesis, we claim that there is an increase in IQ at age 11 compared to age 3. So these kids that are highly creative, they show an increase in IQ. And that was done at the point, this is the 0.01 level, right? 0.01 level. And that's pretty much it. That's how you do, this is how you conduct these, the correlated groups t-test, the computations. You got to find the table. You got to find the critical values in the table, right? That's going to be the critical value compared the obtained value to. This is, go back to here. So my obtained value is here, my critical value is here. This is more extreme than the obtained value, so we reject the null. And that's pretty much it. And so you think of this as as similar, almost the same as the one sample t-test, but instead of X, you have D. Your one sample is the set of the sample of different scores, basically. Now, the repeated measures or the correlated groups t-test also has higher power. So correlated groups T is higher power compared to independent groups. I know it's a little sloppy. To independent groups T. Higher power, statistical power. That means it's easier to correctly reject the null hypothesis. Why does it have higher power? Because there's less variability in the two conditions. And the reason there's less variability in the two conditions is it's the same person, both before and after. So those individual differences don't exist because it's the same person, right? When you have different people in conditions, not only do you have the effect of the treatment, but you also have individual differences. Some people react better to the treatment than others, right? Everybody's different. So there's a lot more variability when you have different people in groups. When you have the same person in a group, you don't have that individual differences because it's the same person. So the variability is decreased, therefore the power is increased. So in a way, if you could run correlated groups, you'd have a better chance of rejecting the null, which we all want to do, right? Our goal is to reject the null. The problem with the correlated groups is What happens if there's something that occurs between before and after that affects the study, right? How would you run a drug study before and after? You give the placebo at time one and then give the drug at time two. Well, then there's order effects, right? The order in which you give the drug may be explaining the difference, right? If you give the drug at time one and the placebo at time two, then there's a history effect because the drug may do something to influence time two. You don't know how long the drug stays in the person's system. You don't know if the drug's going to cause some change in the person that may last a while, may last permanently in some cases. I mean, that's not common. The drug usually leaves the body pretty quickly, but it could because of that gap in time between the before and after. There's all kinds of things that can happen in that gap between before and after that can affect the study. So that's the problematic aspect. So even though this has more statistical power, there's more what are called threats to validity. There's more problems that can happen with the same person over time. And the biggest one is they just don't show up. Right. And then you have to look at it like, are the people that show up for the after, are they different in a way than the people that drop out? And that could be important too. Maybe only a subset of the population is going to do the after. And those people may be somehow qualitatively different than the people that do before and after both conditions. So there's missing completely at random data. It can get messy. So I think the moral of the story is only do this if you're looking for like an intervention. If you can run independent groups t-test, it's probably better. Even though it has less power, it's probably safer to run independent groups t-test versus the correlated groups t-test because you don't have to worry about all these issues that occur between the before and after. So that's kind of the moral of the story. Now, could you run this with different people? Well, there's one very rare, and I'm talking about rare, really rare condition that the book may talk about. Um, if only I can move this without connecting this. Yeah, it's causing me a problem with this thing. Every now and then I get these problems with these lines here. I'm probably doing something stupid here. Okay, it's the lines. Sorry about the lines. I'm not quite certain. I'm just trying to move the page. And I'm getting all kinds of lines here. Keep switching. There we go. I'm quite certain why it does that. I have to figure out why it keeps doing that randomly to me. You know what I could do? I could do a new one. Let's just make a blank canvas here, so there's no that distraction. Okay, so sorry about the lines. One other issue with this correlated groups, uh, one other alternative. So usually we have repeated measures. And these are same individuals in both conditions, right? We talked about this at the beginning. But we can also have something called matched samples. Now, this is really rare. And personally, I've never done a study like this where you have two different people matched on relevant variables and randomly assigned to conditions. So this wouldn't be before and after, but it would be, two different groups that you're running basically the same individuals at. So, like, for example, let's say you had married couples. Now, married couples are probably correlated on a lot of important variables, right? Because they're married, so they should have a lot in common. So, partner one and partner two of the married couple are related. They're highly correlated. So, those two variables are highly correlated. I could then randomly assign one to each condition, each of the two conditions, and I could say that they are matched on a lot of important variables because they're married. And I could treat that as if they were the same person. So when you have a match samples design, you have two different people, but they're related in some way or many ways. And statistically, you treat them as the same person, right? So it's not necessarily a before and after, but it's if you have two other conditions that you want to basically match somebody on. Why would you do that versus the independent groups? It could make sense from a statistical point of view in terms of you increase the power of the study. But these are very rarely done. These match sample designs, and I personally could not recommend doing them. Where you take two people, you match them, right? So they're matched on whatever relevant variable you have, and then you randomly assign them to one or two groups, group one or group two, and then you look at the DV, right? You look at the dependent variable here, dependent variable here, and you treat this as if it's the same individual. So you do get that less variability, right? But it's convoluted, it's difficult. And I've never done a study like this. I only mention it because the textbooks do talk about match samples. They're really rare studies. Like, I don't even know if I've actually read a study that has matched samples ever. I don't know why all the textbooks talk about it, but it's like in real life, it just doesn't happen. Like, if you're thinking about running a match samples design, you're better off just running independent groups. But I guess if you wanted to run like husband and wife pairs and look at, say, what is their response to stress. So you would randomly assign one of the pairs to a stress condition and one of the pairs to a non-stress condition, right? Group one and group two. And then you compare them as if they were the same individual because they're married and they're matched on a bunch of relevant variables, you would think. And you get a little more power there. But to me, like, it doesn't work for me. Like, I would never do this. And I don't know anyone that does match sample design. So I can't really like kill it and say it's a terrible idea. Maybe someone has a good use for it, but I just can't think of any off the top of my head. But I like to bring it up because it is mentioned everywhere about a possibility. We did a match samples design. In 99.9% of the occasions that you see correlated group t tests, it's always going to be this repeated measures. And then you could have repeated measures with more than two conditions. You could have three conditions. So if you have three conditions and you have the same individuals in each of the three conditions, you no longer have a t-test because t-test is two measures, right? Two groups, before and after. You have repeated measures ANOVA, and we're going to be talking more about ANOVA both in the lab. The C ANOVA in the lab, and then we're going to be doing it by hand, and we're going to be doing a very simple one-way ANOVA, but you could have a more complicated repeated measures ANOVA, and there's more assumptions for that. It's a little more complicated, and it'd be pretty difficult to calculate by hand. I mean, it's possible. It's just not worth it, right? You have this issue with this repeated measures ANOVA of something called sphericity, and it's a bit of a mess. You got to make sure that there's uh, the covariance matrix is basically the same among all pairs of levels of the different variables, which doesn't mean anything to you, but it's important for doing the repeated measures ANOVA. So that's just a reminder that there's other, you can extend this out to many conditions. And the more conditions it is, the more complicated the design becomes, the more problems you have with it. And statistically, the more trouble you can also have with it. So, but I just figured I'd mention repeated measures versus mass samples, and that we're almost always using repeated measures design, which is correlated sample t-test. When you have two conditions, it's always t-test. When you have more than two conditions, it's going to become ANOVA, analysis of variance. So hopefully that helps you understand, the correlated groups t-test and the difference between correlated groups and independent groups, both, theoretically and statistically, mathematically, and that helps you. If you have any questions, reach out to me. If not, I'll see you back with more stuff, which will probably be the one-way ANOVA next. So bye for now.